Thank you very much. It's a pleasure to be here. What you've been seeing here on the screen, and I'll run it again, is a very interesting movie. It combines results of some simulations that you see right now, which were done with fairly low resolution, and it's amazing to say they were done more than 20 years ago. But they've been visualized ever since. And at some point, you see these images rotating and freezing, and then they're merging into actual observed galaxies that we see with the Hubble Space Telescope. And these are like this, pictures of interacting galaxies. What's amazing about this movie is that it's a one single old simulation that, seen at different stages with some rotation and progression, can explain a lot of the pictures that we see. So I think it's a remarkable evidence to how well we can reproduce some of the structures of observed galaxies. And this will be the topic of my talk about how it's done and what we've learned and where we're going with that. And I thought that I'll show you more about how simulations work and actually what goes into them. And of course, you know the background for all the formation of structure in the universe is dark matter that collapses and forms filaments, these elongated structures, filaments on large scales, halos in the middle of these filaments, and then galaxies form within these filaments. To an observer, the galaxy looks like this. It has spiral arms, it has stars, it has a lot of gas and dust in between. To a theorist, galaxy is a big dark matter halo that surrounds it with a lot of little stuff that is happening in the middle. And I'll show you how these two overlap and what's the crosstalk between them. In simulations now, galaxies look like this. They're not too bad. We can produce these galaxies. They have spiral arms. We can see colder gas here in the right that's supposed to be forming stars. There are some stars forming in the middle. There's a lot of structure on the outside with more diffuse, lower density gas. Here's an example of one simulation and the other on the other side. But real galaxies look like this. There is much more structure still. The spiral arms are more tightly wound. There is a lot of dust. There's bright, dark spots you see between the bright spots is absorption of light by dust. That is rarely included in simulations yet. There is a lot of gas in those galaxies, and that is still not included in this level of detail in the models. And there are two ways of looking at this. One, you can say, oh, of course, we need to build better models, and there is some progress, but it will take longer time. But there is another way to look at this, and we could ask, how is it even possible that we can make the models right now that look even approximately like the galaxies that we see in these images? These galaxies are extremely complex. They have billions of stars. They have comparable amount of gas. They have very strong ionizing radiation that emanates from those stars. They have dust that absorbs that radiation. There is a lot of material in the cosmic web that surrounds that. So how is it even possible that we can make models to this level? And I think it's quite interesting to consider. And the reason we can do it is essentially because we have, in a statistical sense, knowledge of the initial conditions. And I'm sure you've seen images like this. These are anisotropies in the cosmic microwave background radiation that show us when the universe was very young, the little inhomogeneities, in this case, temperature of radiation, which translates into inhomogeneities in the density of matter, which then grow under their own gravity and produce all the cosmic structure and galaxies that we see. And the reason we can make simulations is because we can take these initial conditions and we can run them through sophisticated models, through running simulations of galaxy formation that I'll talk to you about, and then make predictions for how actually galaxies and stars within them form. Having knowledge of these initial conditions is fundamental. Without them, we would not be able to produce galaxies to the extent that we can now. What we see here is not a real movie. It's an artist's impression of how those fluctuations would grow and how they would form stars. And they're motivated by the results of simulations. But there is a lot of filling in the gaps that needs to be done to really make this picture real and to make movies like this with actual simulations. So how are simulations made? As you probably know, the shape of the universe is a cube. or at least it can be thought so. And the way the simulations are done is by taking a large volume of the universe, so all the matter that began to evolve under their own gravity from all these little fluctuations in a large enough volume, and then evolve it over time and solve equations of gravity and others and see how a relatively uniform distribution of matter early on becomes more and more non-uniform and forms, by the end, the structure that we know as the cosmic web, and galaxies are sitting at the brightest points between those filaments. The reason the universe is cube is because you can solve equations much more effectively for the gravitational potential using fast Fourier transform. And it started the technique for the first cosmological simulations was developed in the early 1980s. And then FFT was a very important method, and it still is. And all those codes were written in Fortran, and they run very fast. And that was really the reason why the universe was taken to be as a cube. But it also makes sense, actually, even if you think about the expansion of the universe, it's best understood in splitting universe in cubes rather than everything else. And I'm not going to say more about this, but if you're interested, ask me at the end, and I'll explain why. So once we have this cube, then we have to solve a lot of partial differential equations for the evolution of matter, and most of matter is dark matter. We don't really know what it is, but assuming it's an elementary particle of some sort, we solve for gravity of these particles. There is cosmic gas, mostly hydrogen and helium, and we have to follow gas dynamics of this gas. And after stars form and produce heavy elements, then we have to follow those as well. And then we form stars, and they become collisionless particles that we also have to follow in the simulation. There is a lot of differential equations that need to be solved. They're all solved on a grid with some approximation. So all differential equations are transformed into finite difference equations, into algebraic equations, which we can then solve. And usually space is discretized in cells, in smaller pieces. And what you can see here, this image actually does not, this grid structure does not correspond to this image. I put them because it's the nicest illustration I could, but it's from a different simulation. So don't look at the scales here, but it shows the idea that you take some regions of space and you divide them all in these cells, and it's a two-dimensional picture, but of three-dimensional cells. And some of them are larger, and some of them are smaller. And you really want to have smaller cells because you're translating differential equations into finite differences. So it's delta x that matters. The smaller the delta x, the more accurately you're solving these equations. But on the other hand, there are numerical limitations. You cannot have too many of the cells because even the fastest computers can only run with so many. Right now, the largest simulations we can do with about 10 to the power of 10 resolution elements, cells or particles like this, which is a fairly large number if you think about even the memory requirements for that. But you can easily convince yourself when you're doing a three-dimensional simulation, 10 to the 10 is not very large. It means in each dimension you have about several thousand, and then cubed, that gives you 10 to the 10. And several thousand is not a very good resolution. We have to go from scales of many megaparsecs, many millions of light years, down to scale ideally of below a parsec, and this is the scale at which stars form. So it's at least a scale of 10 to the 7 in linear dimension that needs to be covered, and 10 to the 7 cube is 10 to the power of 21. This is much larger than 10 to the 10. So there is still a big discrepancy between how many of the cells we can have in the simulation and how many we would like to have. And therefore, these techniques of mesh refinement are extremely useful. We are not splitting all space into tiniest little cells like this. We're only doing it in regions that are of most interest, in regions where we think the matter will reach the highest density, where in our application stars will be forming. There is a lot of material on the outside that sits at lower density. The contours here show approximately the density of the material. At lower density, nothing much is happening. There is no need to split that volume in many, many cells. And therefore, you see here how this adaptive mesh refinement, as it's called, is very effectively putting resolution elements where they're needed and not putting them where they're not needed. And with this technique, we can have 10 to the 10 elements, and we can have a spatial scale of at least 10 to the 6. Not quite 10 to the 7 in one dimension, but 10 to the 6. And this is a huge, huge improvement from algorithmic point of view that allows us to solve these equations much more accurately and reliably. And this is by far not the new technique. It came from aerospace engineering. It was developed in the 1970s. And all the modern planes are built with model testing from these techniques. And you flew on the planes, and therefore you know this works. The flow of the air along the wings of the plane that's the fastest is resolved with the smallest resolution elements. If you're sailors, then you also recognize this. The flow of air along the sails of the boat is the fastest, and therefore to model it, you have to do it with the highest resolution. Far away from the boat, nothing is happening, and therefore you could afford to have much smaller cells. So this is technique of adaptive mesh refinement that really allows us to solve equations more reliably.
So how are the boundaries treated from mesh to mesh? Is it a continuous thing, or how do you, so that the boundaries be adjusted?
Right, yeah. It's not trivial, but it's solved iteratively. So the issue here is when we have the cell and we have potential on larger cell, it has to correspond. The potential in smaller cells, but within a larger cell, has to correspond to the average potential within this larger cell. So at all resolution levels, at all hierarchy of cells, the potential in a given place, gravitational potential and also fluid forces, have to be the same. And this is done by relaxation techniques. So you do it iteratively, and usually several iterations are enough per time step to do it. But that has to be done, absolutely. OK, so this was actually the easy part. Doing gravity is the easy part. In solving galaxy formation, there are a lot more complicated things that we have to deal with just because galaxies are complicated, and that's what we've got. We can do gravity fairly well, and we can study evolution of dark matter fairly well. I'm sure you've seen talks and movies of the evolution of dark matter structure. But then there is more stuff we need to do that concerns cosmic gas and formation of stars from cosmic gas. And there are different pieces here, and I won't go through all of them. This is just to show you all the equations we have to solve. Those in green are understood much better. And it's just a matter of technical way to solve them. Those are in red that have to do with actual formation of stars, and especially the feedback of young stars on their surrounding gas are much harder to do. And I'll show you an example of what it means. Star formation, as it's implemented in simulations, is done in a way that you study the flow of the cosmic gas, and then you see where it gets to very dense regions. In observations, we know that stars form in giant molecular clouds. So if you can form a giant molecular cloud in a simulation, that you can convert a certain amount of gas mass in that region into stars. And of course, we don't have individual stars. We create stellar particles. So these are collisionless particles that represent a collection of stars, and then we can study their evolution. But this process relates to this one, because once you form young stars, they're bright little things. They're bright big things, and they have a lot of ionizing radiation. And then after 3 million years, they explode as supernovae. And those supernovae go and expand into their surrounding medium, and they profoundly affect the structure of the gas surrounding them, from which new stars will form. So it's a chicken and egg, and the feedback is a really good word. Stars affect the gas from which they form, and it feeds back on its own and regulates star formation in galaxies. And we now think that this is one of the most important, or maybe the most important ingredient in modeling galaxy formation. And a lot of the work is going now into really modeling this well. Here's an example. Here is one young star cluster, collection of young stars. These ones you can almost see with the naked eye, maybe not quite, but with a small telescope. In our neighbor galaxy, Small Magellanic Cloud, here are the young stars that formed. And on the outside, you can see the shell of emission. This is the ionized gas that is being pushed by the young stars of this cluster into the surrounding medium. And outside of that, there is a lot of still dense and neutral gas from part of which the stars formed. So this is an example of a giant molecular cloud that is being disrupted now by the stars that formed within it. The chicken egg killing the chicken, or the other way around. But there is a lot of this regulation. And this is what regulates the total star formation in galaxies. And we have to achieve this process in the models that we're making. And not just put it in by hand, but actually make it happen by solving equations appropriately. This is the code that our group is using. It's called ART, which stands for Adaptive Refinement Tree. It's an example of this adaptive mesh refinement code. Here are the equations that it tries to solve. I'll skip it. If you have questions about it, I can describe in more detail. But we try to model most of the effects that were written on the previous slide that have to be part of galaxy formation. There are several groups in the world doing this type of simulations, and there is a race right now. There is a lot of progress that's being done in simulations of this type in the last 10 years, 15 years. And it continues now, and there is a race to get better and bigger and better. And what you can see here is comparison of different simulations on a plot of mass resolution and spatial resolution. And resolution for any numerical study is a key. So mass resolution is the smallest mass of a particle or cell size or a gas particle that we can have in a simulation. Once we have a cube which we're simulating, the total amount of mass is there. We're discretizing. We're discretizing in mass, and we're discretizing in space. So mass resolution means smaller mass particles for the same total mass that we have in that volume. Just means we have to have more particles. But the smaller masses we have, the smaller structures we can resolve, the more interesting parts about galaxies we can learn. Spatial resolution is the same thing. It's technically a different resolution, but smaller is better. We can, again, resolve smaller structures. We can calculate the forces between components of the galaxy better. And the examples of simulations you have in this plot, which are the worst mass resolution and the worst spatial resolution, were done in early 2000s, mid 2000s. And there's been a progress in the last 10 years, even less than 10 years, moving up in scales. And this is logarithmic scale. So factor of 10 here means factor of 10 more particles. It's factor of 10 more memory you need to have. It's factor of 10 more computing time you need to spend on them. And actually, it goes nonlinear with n. It's not easy. With spatial resolution, it's this factor, but cubed. So it's even worse. Factor of 10 in spatial resolution means you have to have 1,000 times more resolution element unless you're doing mesh refinement. So these are not easy steps, but you can see even in 10 years we have this sweep of races. I'll show results from several of this, and I'll just ask you to remember these two names, Eagle and Illustrious, that are fairly good from a few years ago. And I'll mention these results from fire and these results from gasoline. But there is a range of others as well. In previous generations of codes, and that was 2010, so 7 years ago, that's previous generation of codes, most galaxies were formed like this, and you can see quite much detail of them. They look fairly round and spherical or elliptical. And that was the case. We did not have many disk galaxies, and most of the galaxies we observe in the universe are like the Milky Way. There are disk galaxies or even smaller. We could not actually produce them on the computer. The reason for that was partly numerical resolution, but also detailed modeling of star formation and feedback. Things have changed, and these are results from the newer fire simulations of 2 years ago. Here, we do have much more pronounced and thin disks. This is a view face-on. When the disk is face-on, you can see spiral arms. And this is a view edge-on, so this is how thin those disks are, and this is how probably even thinner than the Milky Way is, but there are other examples of nearby galaxies that look like this. So what's happened? What's the change? Numerical resolution is one thing. Stronger feedback that's included in these models is another thing. Stronger feedback means stars are forming more efficiently in small regions of space, and they're affecting their surroundings more. There's more ionization, there is more input onto momentum and temperature and energy of the gas surrounding them. And part of that came from better understanding of how to model these processes. But part of it is not random, but a choice. So having higher efficiency of converting gas into stars was a choice that was made over time. And we don't really have a very good idea of whether it's right or not. It's one of the parameters, one of the knobs you can crank in a simulation and see what happens. And it essentially makes star formation more explosive. And it affects the interstellar medium much more. But we don't really know if it's right. And from what we learn about local observations, it may not be exactly right, but it produces more interesting galaxies. And so it's like, do you buy American or do you buy cheaper, right? It's sort of its balance, and there's nothing wrong with buying non-American. There's also nothing wrong with buying more expensive. But we need to understand what is right and what is not. There is only one case that happens in nature, and we want to understand how does nature do it and model it in that way. And we still can't quite do it. So there are many uncertainties still that remain in simulations, and at least several of these parameters that could be varied that could produce fairly similar results. And then how do you decide what's right, what's not? So because it's such a complex nonlinear system that we're solving, we have to rely on observations, of course, to tell us, to guide us in what's the right direction. And the most important are scaling relations that we observe for a large sample of galaxies that we know corresponds to a variety of systems, not just one galaxy, it's not just one Milky Way we want to form, not one small Magellanic cloud that we want to form. We want to be able to explain formation of majority of galaxies in the universe, and for that we need large samples and certain relations, certain correlations between the properties of those galaxies. So the two that have been most useful so far are the stellar mass-halo mass relation that applies on the scale of a whole galaxy. And the other one is called Kennicotte-Schmidt law of star formation that applies on scales of kiloparsecs, which are large chunks, large pieces of galaxies, splitting it in several chunks. And let's see what these are. The stellar mass-halo mass relation is shown here. This is the ratio of stellar mass to halo mass. So halo mass is the total mass of all material in the galaxy. It includes dark matter mostly, and stars, and gas, and dust, and whatever else is present. So it's a total dynamical mass. It's the mass of that big, dark halo that I showed on the first slide. And stellar mass is the mass of the stars that we observe. So it's always less than 1, and that's actually significantly less than 1. You can see the scale here. The maximum goes to just a few percent. And then it drops as a function of halo mass. And the range here is 5 orders of magnitude in halo mass. It's a very good relation. It's very useful for calibrating the models. How is this relation obtained, right? Well, stellar mass we can measure. We have large surveys of galaxies. We can observe their stars. We can count their luminosity. We have some idea of how to convert luminosity to mass, and we obtain a measure of stellar mass. How do we know the mass of their dark matter halos? By definition, the dark matter does not emit electromagnetically. We do not have a way of detecting it. We can only measure its influence on the dynamics, its gravity, on dynamics of other tracers that we need to have. But far out on the edge of the halo, there are no tracers. It's actually very hard to do it. And the technique that's been used recently that is the most efficient in this is called weak gravitational lensing that looks at tiny little changes in the positions of galaxies that are changing because the light from them is going towards us, and it's passing through the halos of other galaxies, and they create gravitational lensing effect, and they're changing the direction of propagation of photons by a tiny little amount, by the tiniest angle. But taken statistically and modeled with fairly sophisticated techniques at very, very low signal to noise, you can approximately extract information about total mass of the halo that is doing that lensing effect. And this is how we can get information on halo masses. There is an additional way in simulations, of course. We know exactly what the masses of halos that we produce. So we can check for individual galaxies if there is a good correspondence between these masses measured by gravitational lensing and masses that we think they should have. But we can only do it for a few examples, only in the local universe, and for which you can really measure the masses. So it's not very reliable. But this relation, you can see it's plotted for 0 redshift, but you can also calculate it for earlier times when the universe was younger. How can we do it? And this relies on an assumption, but it turns out to be a very good assumption, that says big things are in big things. And you'd be amazed how much you can learn from this principle. You can take it as a principle, as an axiom, and a lot of things follow from it. In this example, what we do is, in simulations, we know how many halos we're forming because we're simulating that. And we can construct how many halos of this mass I have, this mass, and this mass. We can rank them in mass in a given volume of space that we're simulating. And we can do the same in observations. We can look at a big observational survey of the same approximate volume, count all the galaxies, and rank them by stellar mass. And then we say the largest galaxy is going to sit in the largest dark matter halo. And the second ranking galaxy is going to be in the second ranking dark matter halo, and so on, all the way down. And you can do it slightly more sophisticated. You can include some scatter in this mapping, but that's the basic thing. Big things are in big things. And direct measurements of halo mass for a few galaxies that we have actually seem to support this. It's a very reasonable assumption. Once we've made it, then we have correspondence of what galaxy of a stellar mass should have what halo mass, and then we can make this plot. And there is, of course, some observational uncertainty here, some spread, but there are results of many different surveys that show to point to a very consistent picture. It's not just an assumption. We can test this assumption in other ways. What is not assumed here is what would be the spatial distribution of halos and galaxies of this particular mass. So looking at the spatial correlations, that was called a two-point correlation function of galaxies and halos, we can test if this model works, and it actually does reproduce a correlation signal of galaxies at 0 redshift and also in the early universe. So it's a very good assumption. And then it gives us this plot. It tells us that there are some galaxies at some mass scale here that are most efficient at forming stars. And they have mass of about 10 to the 12 solar masses. Galaxies at larger mass and smaller mass are less efficient. That is, for the same total mass, they have less stars. And that is already a useful constraint. That already tells us that in this mass range, the conditions within galaxies are such that they promote star formation more than those in at other masses. And we understand a bit more. We understand that star formation needs to be suppressed in galaxies. It actually is fairly inefficient. What you see here at the top of the slides, this number 0.17, this is the universal baryon fraction. This is looking at the and on large scales at the CMB and what we understand about formation of elements in the early universe. This is the average fraction that each galaxy, each dark matter halo should have in its baryons. And baryons also include leptons and all the other particles. So for astronomers, baryons is everything that's not dark matter. It's a shorthand. The same way as we called metals all the elements heavier than helium, which don't necessarily have to be metals, but that's a shorthand notation. We have a lot of complications in astronomy, and therefore we have to simplify things if we can. So universal baryon fraction, it means that if all the gas within dark matter halos was converted into stars, then this ratio would be 0.17. And you can see that even for the most efficient galaxies, it's just a few percent. It's about factor of 5 lower than that. And for most other galaxies, it's even less. So it's only a fraction, and actually a small fraction of baryons that are eligible to form stars do that, and others do not. And understanding why that is the case is a constraint that we have on all the modeling in detail of star formation that happens in galaxies. By the way, we are sitting in the best place. We are at the peak of star formation, and perhaps it's not surprising for us to exist. Maybe not, but we are sitting in one of the most efficient galaxies that form stars. We've learned something else. There is another scaling relation. We've learned that stars don't form from any gas, which we can already infer from that first relation. The efficiency of star formation is low. So only very dense gas and very cold gas is able to form stars. And especially those sitting in giant molecular clouds that are very dense and very cold and they're self-gravitating and the material within them flows in and forms stars. And we can see it on this beautiful example of nearby galaxies that observes the amount of gas, total amount of cold gas in this mosaic of 9 different galaxies in green color. And then it would merge into distribution of star formation rate, essentially regions in those galaxies that are forming stars. And you can see they've compressed in size. There was a lot of cold gas on the outside that did not form stars. I'll try to flick it back and forth so you can see the contrast between them. But this tells us only a fraction of the gas, even the coldest gas, is able to form stars. And that's another constraint that we can use. And more sophisticated way of describing it is called the Kennicotte-Schmidt law, which compares the rate of star formation in a given chunk of the galaxy, so in a given area of the galaxy, density of star formation, compares it with the density of gas, the total amount of neutral gas, and we think that neutral gas is likely to form stars, but not just neutral gas, it's actually molecular gas that does that. So there are 2 versions of this relation. This one, star formation rate versus the total amount of gas. This one is versus molecular gas, and there is a better and straighter correlation with molecular gas, which spans over also many orders of magnitude. So just like the previous relation, just like the stellar mass-halo mass relation, this one is very useful because it spans over many galaxies, many orders of magnitude in density, and we can use it to test models, calibrate models, and simulations should reproduce it. So those 2 relations have been very useful in the last decade for calibrating these models and deciding which ones are right and which ones are not. But even that is not enough. It turns out that even if you have a model that satisfies those 2 relations, you can still have very different prescription in detail on smaller scales, how you form stars and how strong the feedback is. And for example, I mentioned the efficiency of star formation, how much of the gas is being converted into stars very quickly, and that can vary by a very large factor and still reproduce the other 2 relations. So we still have degeneracy in the results, and we need to do more. And this is where I would like to show you the progress that we can make in the future, in very near future, and actually try to break through this. No, I'm with you. That's
prescriptions like Schmidt-Kennicotte relations. Is that true?
So let me give you this answer. We do what we can, but I absolutely agree with you. What we want to have is solving fundamental equations and not relying on any relation. So those 2 relations that I showed, they're not part of the simulations. They are observational constraints that we use to compare and contrast and refine the results of simulations. What we want to have is to get on high enough spatial scale that we can resolve these molecular clouds that are forming stars, model the formation of stars, and then do the averaging over samples of galaxies and reproduce those relations, or not. But that is the goal, right? They're used as a test for the predictions. In practice, of course, in some simulations, they almost have to be put in if resolution is not high enough. And you do what you can. But ideally, yes, we want to get. And actually, what I want to show you now is how we can make the progress and try to do it in a more fundamental way, or at least get more constraints on a smaller scale that will break this degeneracy between the models we have now. But to show you that there are degeneracies, here are these two other names I ask you to remember, Eagle and Illustris. There are two large simulations with fairly similar physics, similar resolution, a lot of feedback included that should be included, including also supermassive black holes, and their feedback. And they both reproduce fairly well the stellar mass-halo mass relation. So these results for Eagle, these are results for Illustris, and you can see in red lines, that's approximately the scaling for observations, and what's shown in dark colors is the statistical density of modeled galaxies. There is approximate agreement, stellar mass, halo mass, here and there to some extent. But what they do very differently is predictions for the for the gas fraction of the stars, for the ratio of gas mass to stellar mass within galaxies in Eagle and in Illustris, and you can see they're on about the same scale, but there is a difference by about an order of magnitude prediction here versus this. So these are two examples of large simulations that are satisfying stellar mass halo mass relation, and they both claim to satisfy the Koenig-Schmidt law, and yet they make very different predictions for gas fractions. So at least one of them is wrong, and how do we know which one and how to do it better? So the way this is modeled in all simulations so far is we have a distribution of gas in galaxies, and it forms this dense structures. And then instantaneously, based on some prescription and using the equations that are written here, some fraction of that gas is converted into a stellar particle. And for example, this epsilon SF, you see, this is what I was referring to as the local efficiency of star formation, fraction of the gas that locally gets converted into a stellar distribution. But what's happened now in this rush to better and better resolution and smaller scales, we've reached such small scales now of several parsecs, that in order to solve these partial differential equations for the gas dynamics requires time steps that are less than 1,000 years. That in simulations we have now, they require 100 years. And this is compared with 10 billion years, the age of the universe. There are now very small, relatively speaking, ages. Real stars, which we see forming in molecular clouds and observations, are taking between 100,000 and million years to form. This is just the amount of time for the protostellar core to collapse and form a star and begin nuclear reactions within them. So the premise that was put in the simulations that you can instantaneously create a stellar particle is no longer satisfied because we have such short time steps. We're resolving in time formation of individual stars. We're not actually doing this. We're not resolving individual stars, but we should be. So creating particles instantaneously is not a consistent way of modeling it. And the new work that started very recently is trying to fix it. And what it does essentially is it grows these stellar particles, the collection of stars, over time. We're resolving in time accretion of gas onto a star-forming region. And we can follow how, if not individual stars, then pieces of stars or fractions of stars are forming over the scales of hundreds of years. And we can also model the feedback that the stars have, their energy and ionizing radiation and the momentum they impart on the gas. We can study it as this particle is forming. And the accretion of gas ends only when the feedback of the own stars from the stellar particle prevents it from falling even more. So in that sense, we're modeling the process of star formation almost like it is happening in observation. There are still numerical limitations, and there are still a lot of things that are simplified. But we are getting into this time-resolved modeling of star formation as it actually is happening. And this way, we can treat these individual particles that we form as star clusters. In observations, we see collections of these bright stars, very, very compact, and they're called star clusters. And there's a variety of them. They're young, they're old, they have a range of masses. and we know a lot about them. And it's for the first time that resolving formation of these particles and star clusters, we can say that the masses we obtain for them in the end are actually corresponding to masses of individual star clusters. In all the previous modeling, it's only the sum of total particle masses would represent the stellar distribution. Essentially, there were tracers of the distribution function of stellar mass, but individual mass of the particle created instantaneously was meaningless. In this case, individual masses actually calculate itself consistently, and we can use that as a very powerful probe. And I'll show you very briefly why. The compact star clusters become very important mode of star formation when it is very active. What this plot shows is the fraction of all young stars that we observe in our galaxy and nearby star-forming galaxies that are forming in this compact configurations of star clusters versus the rate of star formation per unit density. And when star formation rate is most efficient, is at the highest density, the fraction of stars in clusters, these points, gets to very high value, to 50 and 60%. So majority of stars in the most actively star-forming regions in all around us that we can observe is forming in these massive star clusters. And what's more, amazingly, the mass function of these clusters is almost uniform. The mass function is the number of clusters as a function of their mass. They vary from 1 million solar masses down to about 1,000 that we can measure, so it's still quite a large range. The observed mass functions are very close to power law, with a certain cutoff at high masses, and they're described by this function, by a power law with a slope of about -2 and an exponential cutoff. And it's true in our galaxy, it's true in all nearby galaxies. The slope seems to be universal. In all galaxies we observe, we see a slope close to this. This cutoff mass is environment dependent. In more massive galaxies, it appears to be larger. In low mass galaxies, it appears to be smaller. But the slope is the same. Since now in simulations, we can measure individual masses of the star clusters, we can see if all the models, if we vary our parameters that give the same predictions on large scales, we vary them and we see if they would make the same predictions for the mass function of star clusters, but now on much smaller scale. The star clusters have sizes of a few parsecs. They're 1,000 times smaller than the previous scale in which the Kennico-Schmidt relation was measured. Going down factor of 1,000 in scale is a very strong constraint. And here's first preliminary result from the simulations. We can make that vary a lot of parameters about the feedback and efficiency of star formation. And most of them produce the shape of the mass function that is similar to observations. We actually can reproduce this amazing trend. But there are some in which it's very different. And this one in particular has very different local efficiency of star formation. And we can say something about whether this is the right way to model galaxies. It's still, this model reproduces the previous two scaling relations, stellar mass, halo mass relation, and the Kennico-Schmidt. But it fails on this scale. We can begin to differentiate the models by using the smaller scale modeling of star clusters. We can also see from observations that this local efficiency I mentioned, this epsilon freefall, is actually measured to be very small. This is a compilation of many star-forming regions, and it's a comparison between star formation rate density and the gas density, and the constant of proportionality between them is that epsilon. And it's measured to be about a few percent, 1%, a few percent, on global scales over, again, many orders of magnitude. So we can run these models with different efficiencies and see, OK, this one does not work very well. Maybe this one also does not work very well, but something in between does. And we can try to really see what is the right value to use in simulations. It's a very important discriminant. We can understand the origin of this mass function. I'll skip it for now, but if you're interested, please ask me. We can understand why the mass function of star clusters has what's called this Schechter shape of the mass function, power law with exponential cutoff. And we also understand that the maximum mass, the cutoff mass of star clusters, does scale with the overall star formation rate density. So larger galaxies have larger star formation rate, and therefore they produce more massive clusters. It essentially is the same application of the rule, big things are in big things. But here we can quantify to what it is. And the final thing I wanted to show you, additional constraint that comes from the star clusters. What we also observe about them is the amount of time it takes the stars to form. So I mentioned each individual star takes between 10 to the 5 and 10 to the 6 years to form. We can take a collection of all the stars in the given star cluster that's just formed and look at what is the ages of stars that formed just recently. What was the history of their star formation? What was the spread of ages of the stars that just formed? And the spread of ages is of the order of a few million years. So there's been some difference, but it's between 2 and 3 million years for majority of nearby star clusters where we can measure it. And therefore, we can use this constraint on the age also to constrain the models. And how can we do it? Because if you think of this, again, efficiency of star formation, this epsilon freefall, it essentially says how quickly gas is converted into stars. If this efficiency is very high, then very quickly I have the amount of gas in my dense region. It's being converted into stars. And all stars that would result would have very small spread of ages. They would all form within a very short period of time. If, on the other hand, this efficiency of conversion of gas into stars is very low, it will take much longer time for the gas to be processed into stars. And it will take not 1 million years, not 2, but more. And here's comparison of several models of efficiencies of 1%, 10%, 100%. And of course, the formation time shown here for a distribution of clusters. And let's just look at the median, where this one is 50%. It doesn't scale linearly with this epsilon freefall, but it scales some. And this is 100% efficiency, 10%, and 1%. And you can see systematically the ages of clusters, how long it takes to form them, increases. It increases between 1 and 3 and maybe 5 million years. So again, we can use the observed distribution of ages of stars in the cluster to try to constrain these models and say, OK, well, maybe this one is not right. Maybe this one is too fast, but this one is just right. So sort of finding this Goldilocks is what we can do now with this method. So let me finish here. I think the main result I would like you to take away from this is that there's been a lot of progress in the modeling of formation of galaxies, but there is still a lot of, and that should be celebrated many, many times. But there is still a lot of degeneracies that are left in that modeling and different approaches and different groups. And what we're trying to do now by going to much smaller scales of star clusters is to break the degeneracy. And we've had a lot of progress in 10 years. I'm very confident in the next 10 years, even 5 years. If not solve it completely, we'll have much better understanding of how to produce these beautiful images of galaxies that I showed you in the beginning. Thank you very much.
So a lot of people, observational astronomers looking at feedback are trying to measure the gas and the gas kinematics and test models that way. And I wonder if you could say anything about what the models, you didn't really talk about what you mentioned feedback, but predictions about the gas and how you would, what's the best way to trace it and that kind of thing.
Yes, so I'll be happy to tell you more about this later, perhaps maybe over a few beers. But the main trend you can see, and well, let me just get to the previous plot. The reason why there are different durations of star formation as a function of efficiency is that with very high efficiency of star formation, you terminate star formation faster. There is actually not a fixed amount of gas that's available for star formation. More can flow from the outside if you consume some in some dense region. More will flow in unless you push it back. So this high efficiency of star formation makes more explosive star formation, much more violent way of preventing new gas from falling into star-forming regions, which results necessarily into larger velocities of gas that is outflowing from those regions, and in some cases to more than 100 kilometers per second. And this is a systematic trend. The lower the efficiency of star formation, the lower the velocity of outflows you would expect. So if there is a good way to parameterize it observationally, then it would just become another test of these models.
So I have a question regarding the stellar halo mass relationship. So you did show one plot that showed the eagle and illustrious simulations and the stellar halo mass relationship. And you did mention a few times that mentioning how your simulations will reproduce those same plots. But the thing that I'm worried about is how reliable is that relationship? Because looking at those two plots, there was quite a huge spread for a given halo mass, with stellar mass for a given halo mass and vice versa, 2 orders of magnitude. So I'm just curious, like, how reliable are those relations when you're using them to, for example, compare your simulation or reproduce them?
Right, no, you're absolutely right. All these relations that I mentioned have significant scatter. I don't think it's 2 orders of magnitude, but there is a factor of 3 at a given mass. And this is exactly why we cannot take one galaxy and simulate one galaxy and compare it with one observed galaxy and see if they match or not. We have to do it for a large sample of observed galaxies and modeled galaxies and see if statistically we get similar relation. It's only with statistics you can beat down the individual scatter. But it's present, and it just tells you that it's not only the halo mass that determines the final stellar mass that the galaxy will have. There are many other factors that affect the formation of stars. It just appears that the halo mass is the most important parameter, but all the others definitely contribute to that scatter. That's just part of modeling, and actually correct models should reproduce the observed amount of scatter. It should not be less than that. Well, it's very hard to tell, right? It's unknown unknowns with observations. But there is a fairly consistent picture now, and surveys are getting larger and larger. I think at 0 redshift, we understand it pretty well with that scatter of about factor of 3. At higher redshift, it's of course, observations are much more incomplete, and therefore the inference is also more incomplete. But oh, it's real, yeah, of course, yeah. It's definitely not one-to-one relation between the two masses, of course.
2 related questions. One is, let's say in the next 5 years, what is the mass resolution it can be? And if you go to this high resolution, what physics you would expect to change, to model it?
Oh. Well, as you know, ignorance is bliss. And the more you know, the worse it gets, right? It's definitely true of observations. The more detailed observations you get, the picture becomes completely messy and you cannot explain it anymore. It's the same with mass resolution. Actually, on spatial scales, going to better than what we have now is very dangerous, I would say. And maybe it's too conservative, but on scales of a few parsecs, we can still treat hydrodynamics of the gas as just hydrodynamics. On smaller scales, in giant molecular clouds, we have to include magnetic fields. And we have to treat dust in a more sophisticated way than we're doing now. We have some simple modeling of dust, but we have to do it more. And resolving alpha and wave timescales are much, much worse than the hydrodynamic timescales. So that would make simulations more difficult. In terms of mass resolution, yeah, having smaller dark matter particles is good. And that will happen probably by several orders of magnitude. But spatial scales are more difficult. So they would require solving many more equations than we have. And it's not even obvious that for the purpose of understanding global star formation, it's needed. For the purpose of modeling individual star, yes. But that would require more work. For the purpose of global properties of galaxies, maybe we're still OK sitting at the scale we reach now. But of course, it's very dangerous to make predictions about the future. So in 5 years, you can see what happens.
With the number of parameters you're dealing with, are you worried about degeneracy?
Yeah, of course. So it's inevitable, and just going to smaller scales and trying to have more observable tests is one way to try to deal with that. But some degeneracies will always remain. It's just we're dealing with very complex system, and we can never be completely sure we're doing it right. We can only be sure that we've done it right so far with the tests we've implemented. But we do what we can.
Can you use some kind of pilot so that you get rid of at least some of the degeneracy, just constraints from observation?
Well, we're using constraints from observations, but if we want to do star formation reliably from first principles, we have to resolve flows of gas and formation of self-gravitating clumps and formation of stars from them. We're testing it against observations. We're using guidance from observations into which direction to go, but it needs to happen self-consistently. That's the goal. But there are lots of numerics, of course, and there are degeneracies between the parameters. Sure.
It's just a general question regarding simulation. So in the beginning, you were talking about how simulations are basically we model the universe as a box.
Right.
My question, and probably you did mention this, maybe I missed it, is that so you're simulating whatever's happening in the box, but as things are moving around, things would also be leaving the box. How do you keep track of what comes in and out?
Exactly. This is a very good question, and this is exactly why the universe is a cube. And this box uses periodic boundary conditions, which means that the left side of the box is the same as the right side of the box. So if we have any material leaving the box this way, it magically reappears with the opposite velocity this way. But it's not a random trick. It relies on the universe being uniform and isotropic on large scales. And by this assumption, you can imagine if you have a cube like this, and you put another cube next to it.
Not me.
No. You can be an assistant. No? Okay. Okay, and you imagine this to be cubes, as they should be. So periodic boundary conditions means that this side is the same as this side, but being uniform on large scales means that if this is a representative chunk of the universe, then this cube is the same as this cube. And now I'm going to merge them, slide them like this, and for you, left side of this box is the same as right side of this box, which is the same as the right side of this box. And therefore, this is why the two sides are the same. Which also means that we can only apply these cosmological simulations for large enough volume that it's representative that on this scale, the universe is actually uniform and isotropic. But it's an important assumption, but that's how we keep the mass constant.
Okay, let's thank Oleg Gnedin.